Application Explorer.
There are sheets that you can pick up at the front. There's just one sheet. There's two piles. But if you want, they're just notes shrunk down to a nearly unreadable size so that it's just a reminder for you. Is this working? Is this working? So this is, if you can hear me in the back, raise your hand. Woo. So I don't need to worry about this thing? Yes? Okay, good. Okay, welcome to Computer Science 221. It's a course about algorithms and data structures. Let me just start by acknowledging that we are on the traditional and ancestral and unceded territory of the Musqueam people. I'm thankful to be able to use this space to teach you about something like computer science, which really wasn't around back then. But anyway, that's what we're talking about today. We will be talking about for this semester. My name is, introductions. Here we go. My name is Will Evans, and you can call me whatever you'd like, really, but usually Will works really well. And I will not, you don't need to call me Dr. Evans, because that's my dad. And you don't have to call me like Professor Evans, because that's my brother. So you can just call me Will. Let's see, what else? Oh yeah, you can see that we are a team teaching this course. Cinda and I are teaching this course, and there are 3 sections which run back to back. So if you, for example, sleep in and you miss this one, not a big deal, because we're going to try to be in sync. And we'll be teaching the same material, but with different slides and things like that. So you can skip, go to Cinda's. If you miss Cinda's, you can skip and go to mine. If you miss that one, you can just, go to sleep. Anyway, that's where they are, and that's what times they are, just so you know. We have lots of TAs for the course. There's so many that I don't even know who they are right now. And there's a website for the course. Now, the website, oh yeah, I put this, I see, I cleverly put this pen in my pocket. The website contains all of the lecture notes that I show here, and I'll put up the annotated ones after class. I'm recording this lecture right now on my laptop, so you get to hear my voice and you get to see the slides. So that means you never have to come to class, because those will be posted on the website as well. However, if you don't come to class, there's no interaction. So the point of this class is really interaction. Speak out, ask questions, get engaged. So to help do that, we're going to have times during the course where I'm going to ask you to do stuff in class. For example, right now, I introduced me to you. Why don't you turn to somebody next to you, close to you, maybe somebody you don't know, be brave, they're in the same boat as you, and introduce yourself. Now, somebody that you can work with, somebody that you can ask questions to. Please, go ahead. Okay. I can already tell this is going to be a great class. It's going to be fantastic because of the interaction. In fact, there's so much interaction, it's fantastic. You're doing a great job. But let me write down some other things on this thing. There's not only is there this website, but I also have to remind you and me that there's also Piazza for posting questions and getting answers. Piazza is monitored by all of you, and then all of the teaching assistants and the instructors. And so if there's a way to get a question, that's the way to do it the fastest. Don't send me email because I have to tell you, I go to sleep. And I actually sleep for something like 8 hours a day. That's just crazy. You aren't doing that. But that's what I do. And so you'll probably hit me right at the time when I'm sleeping for 8 hours, and then you'll be upset because there will be 8 hours delay in getting a response. Send it to Piazza, post it on Piazza, you'll get a much more rapid response. I know. There was somebody that was posting on Piazza at 4 in the morning this morning. I got up at 6 and I was like, whoa, that's pretty good. Okay, so Piazza. The syllabus, the lecture notes, the schedule, everything else is on the home page for the course. Do you guys have any questions yet? No. This hasn't been anything to ask about, really. Well, if you do, just let me know. Okay. That's not what I want to go to. There we go. This is the coursework on one slide. So we're going to have labs, weekly labs. They count 10%. So it's like 1% per lab. There's about 10 labs. There's a written homeworks. There are about 15% for written homeworks. There are 3 of them. Each written homework then is 5%. There are 3 programming projects worth 20%. There's 2 midterms. They're on October 10th and November 7th. They're at 6 p.m. They are not here. I don't know what room they're in yet, but I'll let you know as soon as I know. And there's 1 final exam, which is worth 25%, and nobody knows when or where that final exam is. It's not like I know and I'm not telling you to make your life miserable and my life miserable. It's just that the way that UBC works is actually very cool. They allow you to sign up for any classes you want, as long as they don't overlap, like you're not sitting in this class at the same time as you're sitting in another class. They allow you to do that. And then what do you think they do during all this time when we don't know when the final exams are? What do you think they're doing? Any conjectures? Yeah?
Making sure no final exams overlap so no 8 a.m. classes overlap with any other 8 a.m. classes.
That's right. They're running an algorithm to determine how much overlap there would be if they scheduled exams on certain days. And they're minimizing the overlap. So you guys, I know it always seems as though it happens every year, but really, they're trying to minimize the successive final exams that you have to take all one in a row or even one on top of another. They're running an algorithm to do that, which, I actually have to feel kind of good about, considering the topic of this course. But it does mean that we don't know anything until they run their algorithm. And that can't be run until people figure out what classes they're in, so it takes a little bit of time. Okay, that's that. Questions? Not yet. Okay, whoops. See, that's the thing, is control of this is not so great. Oh yeah, collaboration. Well, this is much better. Collaboration. Not only are you allowed to collaborate in groups of 2 people, but you are encouraged to work in groups of 2 people, because there's all the studies that show that sort of pair learning is really effective, especially in environments like programming environments, where you have a programming task that has to be done in a new language called C++, and you maybe can learn more from your partner than you can from me or from a TA just by working together. This is true for written assignments, it's true for programming projects, it's true for lab work. You can work together. The only time you can't work together is on exams. I mean, we could have that, but it's really confusing. It's hard to do. It's hard to coordinate. You can also collaborate with other people, but you have to follow the course rules for collaboration outside of your team of 2, which basically boils down to you can talk to them, but you can't record anything, and you have to take a break afterwards, so you're just not like, just copying what they told you. You can't do that. You have to take it in, take a break, and then write down your answer, okay? Something like that. Okay. You're good? Everybody's good? Let's see what's next. Oh yeah, now we can start. So, oh wait, let me check to make sure I didn't do something wrong. Oh, I forgot to tell you something. Right. You have 2 textbooks. Which I neglected to write down on the slide, but I wrote down on my notes. So there's the Carano and Henry, which is the data structures and algorithms in C++. So this is sort of the C++ book. And then there's another book, which is the math book, which is the EP book, which probably you have. Do you have the EP book, or you had the EP book for 121 or something like that? Or yeah. Anyway, it's a discrete math book. Now, I have to tell you, if you don't have these books, it's not like we're going to ask on an assignment to solve problem 17.3 from EP page 228. We're never going to do that. So if you don't have the books, you could get by without these books, because there's lots and lots and lots of online resources for data structures in C++ and for discrete math. These books happen to be reasonable books. They're okay. But if you have a better book, or if you just want to use online resources, that's fine with me. Yes?
Sorry, I just can't see the spelling for yourself.
Oh, thank you. He is exercising his right to tell me when he can't understand what I'm doing. This is the first person that did that, and you should feel free to do this. It's what you're here for, is to learn. And if you can't read what I write, or you can't hear what I say, or you just want me to repeat something or ask a question, this is for you. It's not for me. I've done this before. It's like, I know this stuff. But you ask me, okay? So great. So you can't read, but this is fantastic spelling. It really doesn't get much better than this. Are encouraged to, and that's Caro. Well, I can't even read my own writing. Toronto. That's an N-O. Toronto. Okay. You know, I got comments on my last teacher evaluations, which, by the way, I just got like 2 weeks ago from, never mind, you don't want to know. And one of the comments was, sometimes we can't read his writing. I was like, I told you on the first day, if you can't read my writing, I will slow down and write better. So I'm telling you, ask. That's what we have to do. I mean, anyway, it's like a two-way thing here, communication. Okay, any other questions? Yeah.
Also, will these two textbooks be made available on the course website?
You mean an online version of the textbook?
Yeah.
No. And do you know why? Because somebody's trying to make a lot of money selling you a discrete math textbook for, I don't know, $100 and some. That's why we're trying to reuse it for multiple courses. Even though it's a good textbook, it's kind of ridiculous that it costs that much money. I don't know. But we can't put the online versions up because that would be bad. But if you don't have them and you don't want to get them, that's okay too. I mean, there's never going to be a, maybe you'll learn something from them. I know, for example, EP, the reason why we use EP is it's an excellent section on asymptotic analysis and examples of recurrence relations and things that you use to solve, to find running times of algorithms and things like that. It's an excellent section on that in that book. But you can find that online too. Okay. Now we get to go. Okay, so typically this would be the first slide of the class. Typically there'll be announcements. Homework 1 is going to be available soon, by this Friday for sure. It will be due a week from then, September 13th. There are no lab sections this week. Labs will start next week. So some announcements like that. And then the plan for the day. And the plan for the day today is to introduce algorithm analysis and introduce a little asymptotic notation. Okay, let me tell you another fact, which is I am ambitious. And when I write down the plan for the day, I hardly ever make it all the way through the plan. But I figure it's good for you to see what's coming. It's good for you to see what the plan is. But don't panic because we may not make it through all the notes that are on your sheet. Don't worry about that. It's not like I'm going to pretend that you should know that from just a sheet of paper. We're going to talk about it, but it may not be today. As you can tell, this is not exactly scripted. So anyway, this is the plan. And often we'll have a warm-up exercise. Today we don't have any warm-up exercises because I figure everybody's warmed up. So this is today's plan. And in fact, I'm going to cheat a little bit because even before we start today's plan, we're going to do something else first. But first I want to ask you if you have any questions about the sort of course logistics, like how things are going to work. Was it clear enough from my, yeah?
Is it just like the alternate between a programming assignment and then a written assignment?
Good question. Do we alternate between a programming assignment and a written assignment? The answer is no. What we do is I give you a programming assignment at the same time as you have a written assignment. I really do that. But I'll give you 2 weeks to do a programming assignment. I'll give you 1 week to do a written assignment, and I'll let you juggle out how you want to do things. But basically, you'll be working on about one thing, and then there'll be an overlap on a weekend usually. So if you finish one early, like a written assignment, then you'll have another weekend to work on the programming assignment. Or you can decide how to balance your time. If you need more time for one or the other, I figure you know it better than I do. So basically, I'll give you, as soon as I can get the stuff out, I'll give it to you. And then, however it works. Yep.
I was wondering for the partner work, are the two partners allowed to submit the same thing? Or?
Usually what happens with programming assignments is you submit one version. Usually with written assignments, you submit one version.
Okay.
Usually with labs, I don't remember.
So
Maybe
as
two.
it's like a specified partner, it's okay to have like really similar stuff.
Yeah. But really similar stuff means the same stuff, right? Like for programming assignment, you're only submitting one programming assignment. Yes, this happened once. I ran MOS. You know what MOS is? No, you don't know that because you're not an instructor. Let me tell you what MOS is. MOS is the thing that looks for plagiarism. I submit all these programs to MOS, and MOS says, these have a 96% similarity. After it figures out, for example, you renamed variable names and you re-indented things and you moved functions around, blah, 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 blah. It says 96%. This really happened, 96%. And I said, oh, great, because I don't like dealing with this sort of stuff. So I brought in the two people and I sat them and I said, okay, what's going on here? I got a 96% match on this programming assignment. They said, well, we're working together as a team. I said, don't submit two, especially when you submit two which doesn't reference the other person at all. It's like you should submit one and with two names on it. Anyway, now you know. Yep.
So I just wanted to learn, like, are labs and partners or individuals?
Yeah, you can do labs and you can do labs as partners, but I can't remember if you have to actually do something individually in that situation. Like maybe there's some sort of thing. I think it's the team talks to the TA, but let me get back to you because I don't know. It's changed. Things have changed a little bit.
So these assignments, can we have partners from different sections?
Yep. And you can change partners during the year. And I'm not going to assign partners. And what else? What other freedom would you like? You can't take a partner that's already taken a class. I mean, unless they failed it and they're taking it again. Yeah. Okay. What is this course about? So this is the sort of a segment. This is not on the plan. It's not part of the plan. This is just to tell you what the course is about. The course is about Rogers Arena. No. Suppose that you went to Rogers Arena to a hockey game, and you found somebody's wallet. And his name is Roger, which is odd. It's his arena. But anyway, you got Roger's wallet. You need to find Roger. I would like you to take a few minutes, turn to your neighbor, and discuss how you would find and return Roger's wallet to Roger. Now, I know, they have lost and found places that you just go and take the wallet to the lost and found, and everybody's happy. Right? That's why they have lost and found. Suppose they didn't. Now what would you do? You can discuss. I'll give you maybe like, I don't know, 2 or 3 minutes or something. Figure out something you would like to do to return the wallet. recording part to this thing. It's not just chit chat. Eventually, at some point, I'm going to ask for people to report. Anyway, go ahead. I didn't mean to interrupt. And I did. So if you figured it out, if everybody's done, then we're done. Everybody good? Anybody like to share their really cool idea for how to find Roger? You have his wallet. You don't have his cell phone because if you did, then you could. No, you couldn't because he doesn't have a cell phone. Yeah.
You could go, hypothetically, Roger bought a ticket, correct?
Hypothetically.
And hypothetically, that's probably do things like, okay, you've got like a picnic stuff, so to speak, that the owners of the arena would have. So you could say, hey, I've got a wallet, here's his full name. You look up his ticket, and then from that, look up where he lives.
I love it. Even if you have a ticket, you even have a seat number. You could go directly to Roger and say, hey.
Well, I don't know if the game's still on.
Oh yeah, it is. See? We got time. It's okay. Maybe he's gone home though. You're right. He could have gone home. Excellent, excellent. This is an excellent solution to this problem. You need to appeal to a higher authority that has information that you don't have. You get that information, which is it's conveniently encapsulated in a ticket, which is a nice little thing. And you can find Roger with the ticket. Anybody else have other mechanisms for doing this? Because what happens if it's hard for you to find those people that actually take the tickets after the game is started because they all go to wherever they go. Yeah.
The stadium's kind of split into sections, so you can go around and show a person from each section, like the idea project, and just keep going around until someone finds Roger in their section.
Excellent, excellent, excellent. Sequential search. Go walking around to every chair. No, you want to go to every section. So maybe a slight bit of parallelism in there. But something like going around to everything and looking and seeing if you can detect Roger by this system. This is going to take a little bit longer. But with parallelism, like you're going to go to sections and talk to somebody in the section and say, hey, but you have to give them the thing so they can show people.
Just show it.
Yeah, this is an interesting. It's a good idea, though. It's a good idea to have parallelism. I'm not sure we could take a snapshot with your phone, and they could take a snapshot with their phone, and they can take that phone. It'd be like pictures of Roger all over the entire arena, spreading out rapidly to cover everyone until Roger says, hey, that's me. Oh, it looks like my wallet. Oh, I don't have my wallet. And then he would say, it's me. That's a perfect idea. It's excellent. Yes, no doubt.
Maybe a way to optimize that is like you would have the speakers, so that we could just say, hey, Roger, we have to walk.
Broadcast. Isn't it lovely? Broadcast. In this case, this is what they do sometimes. They say, excuse me, there's a 4-year-old child who needs their parent. She says her name is Amy. And then, but yeah, it's broadcast. Broadcast mediums are great, very effective in situations like this, where everybody can hear, if everybody can hear. But it's very expensive. Broadcast is extremely expensive because it means that all the announcers who are yakety-yakketing about the hockey game, they have to stop. There's silence. You don't know what's going on in the game. They broadcast the name. Anyway, it's costly. There's a cost associated with that particular approach, which is different than a time cost. It's a resource cost. So this is another aspect of this course. We're going to be talking about cost for how to solve problems. And we'll look at different types of cost. This one is a resource cost, which is a broadcast medium, a very expensive resource, but a good suggestion. There was time cost that we had. There was actually information cost. We need to find somebody with information to help us out, and maybe that person isn't available. Any other suggestions for what to do? Yeah.
This is really crazy. But
oh, good.
If you could stop the event and you made everyone line up alphabetically and just be like, we're looking for a Roger, and then all the Rogers stand up and say, hey, I'm Roger, and you just show them the wallet.
Okay, that combines a broadcast mechanism with an algorithm for sorting people, which I kind of like the algorithm for sorting people by name. Rogers go all together in a clump. but it is kind of crazy. I mean, actually getting everybody out of the seat in an arena is kind of a scary prospect, fire codage-wise. Wait a minute, I gotta make sure we're doing stuff. Okay, we're doing good. Anybody?
You could ask people right in front of you and right next to you if you know a Roger, and if you are a Roger, you can come to the back of the stage in front of you.
And then what are the people that you told to?
They would have to ask people in front of them and next to them, so that they would have the word to everyone in the stage.
Oh, I love this solution. This is the parallel solution. This is the real parallel solution. You start with one person and they sort of talk to their neighbors. And then that one person talks to their neighbors. And the next person talks to their neighbors. So you were talking about a coarser version of the parallel. This is like the very fine-grained sort of thing. Say, where's Roger? Are you Roger? Are you Roger? Propagates, how long does this take? It depends on how big the stadium is, the number of people in the stadium. Certainly it depends on how big the stadium is. That's true. What else does it depend on, this lovely parallel solution? Yeah.
Depends how far Roger is from the original person.
It depends on how far they are. How would you measure distance in this case?
Euclidean distance.
Ooh. You just wanted to sound smart? That's a good one. Euclidean distance. I mean, it's people distance. How many hops do you have to make to get to Roger, right? Like if I turn to my neighbors, and I say something to them, then they're going to turn to their neighbors and say something to them. It's like the number of neighbors that you have to go through until you get to Roger from where you start. That's the time it's going to take to get Roger to say, yeah, I don't have my wallet. So it's a distance measure based on number of hops, like in, for example, routing packets in a network, which we'll talk about when we talk about graphs in this course. Isn't this cool? This is a great problem when you really think about it. Here was another solution. This is the crazy solution that I thought of. Crazy solution. Facial recognition with a drone. Everybody goes to hockey games with their drones, right? So you get your drone out, and you program your drone to like take pictures of everybody. It's going flying around taking pictures of it. It's doing facial recognition with the little image of Roger from his 1983 driver's license, and seeing if you can find it. That's crazy too. That's a weird solution. Any other weird solutions? Any other? Okay. So this course is about this. If you're like slightly, mildly interested in solving problems, like these types of problems, these are computational problems, these are problems that require a procedure, this is part of what this course is about. There's another part of this course. Suppose that you were looking to buy a closet. Let's just suppose you're looking to buy a closet organizer. For example, you could purchase my closet organizational skills, which you see on the left, or you could purchase my mother's closet organizational skills, which you see on the right. Which would you like to do? The same contents. These closets have the same things in them, but they're different. And why does it matter?
If I wanted something from the right closet, I could find it right away and just pick it up. Versus the left, I'd have to be like searching through it to take my time.
I tell my daughter that all the time, and yet her room looks worse than that. It's a big pile of clothes. You're right. It's access. Like, for example, search. If you want to search for something, it's better to search in organized data than it is to search in unorganized data. Better meaning faster. The question is, how do you want to organize the data? Now, you can see here there's some sort of color organization going on, and then some type organization going on, and there's organization by different categories in this particular case. But this is exactly what this course is about. Data structures are ways of organizing data so that you can do things faster, more efficiently, better in some way than you could if the data was unorganized. That's what this is all about. Data structures and algorithms, it's about finding Roger, and it's about organizing closets, but for computers. And what we need to understand is how to measure the success of organization in affecting running times of algorithms. How can you make them faster? And we have to understand algorithms how efficient they are. Do they use a lot of memory? Do they use a lot of space? Do they use a lot of expensive resources like broadcast? That's what this course is about. It's all about that. Trying to figure it out. And in addition, there's one overarching thing besides efficiency in all of this. In fact, it's the first primary thing we have to worry about, and that's correctness. If you write an algorithm or you write a program to solve something, you want it to be correct, because it doesn't matter how fast it goes if it's wrong. It has to be correct. So that's another aspect of analysis that we talk about in this course. So this is the big picture of this course. Is it good? Are you happy-ish? At least reasonably happy-ish. This is the sort of what I just said, kind of in more formal words. Programs manipulate data. They gather information. They organize it in some way. And the programmer, that's you. So I wrote down the programmer, but really, the programmer, this thing right here is you. You decide how to organize it. You decide how to put it together. You decide in order to make things more or less efficient. Your decisions matter. And then it matters because the choice influences correctness, it influences execution speed, it influences memory requirements, it influences how easy it is for somebody to understand your code so that they can modify it. So it's a big deal. Have I told you how much I like this course yet? Let me just tell you that I really like this course. And I'll tell you why. Because it's the first time really that you're getting together programming and analysis. And that, in my mind, is really what computer science is about. I mean, you can be a programmer without knowing much analysis, but your programs aren't going to be good. You need to have that, at least some understanding of the analysis in order to make good choices when you're a programmer. And to know when choices don't matter. You know, does it matter if I do a for loop here or if I do recursion? No, it doesn't matter. Or maybe it does. So that's the sort of thing that we're talking about in this class, is what impact those decisions have on your code. Okay. Here are the goals. You, at the end of this course, are supposed to become familiar with fundamental data structures that are commonly occurring in lots of programs, and learn when to use them. Also, you'll learn something about common algorithms. We'll analyze algorithms like sorting algorithms. Lots of sorting algorithms. You'll be tired of them. And the goal here, though, is to understand a particular problem like sorting, a very well-defined problem, but to understand how well you can solve that problem efficiently, how efficiently you can solve it. And another goal in the course is to improve your ability to solve problems abstractly, which means without just sitting down and typing, you can think in your mind abstractly about how you might construct a solution using building blocks that are larger than the primitives in the language that you're programming in. So that's the other nice thing about this course. You're learning a new programming language, or maybe not, but C++ is not something you've seen on this curriculum yet. And you're learning C++, you will be learning C++ largely on your own. Now, I know, that's kind of scary, but let me just tell you, it's good. I got comments in my teaching reviews about we need more time in class for the instructor to teach C++. No. You don't need more time in class for me to teach you C++. You need to be able to pick up new programming languages because they happen all the time. And you can do that. It's not something that's out of your grasp at this point. And it's a fantastic power. You can start seeing commonalities between languages and how you can learn things and what things you can take advantage of efficiently in different languages. It's great. But your abstract thinking can be independent of the programming language. That's what makes it abstract. Oh yeah, you get to analyze algorithms, you get to prove correctness, you get to compare running times and space complexity. And if at this point, oh, by the way, there's I can read down here. I don't have to keep looking up there. This is cool. Yeah, but I can't really read that. But the thing that I wanted to explain, right. For all those people in there saying, well, yeah, great, this is all like one of these theory classes, it's never going to be applicable to anything that I do. I'm an excellent programmer. Let me just tell you that every year, well, it's like 4 years later, no, 3 years later, no, 2 years later, anyway, people come back to me after they've taken this class and they say, Will, that was a great class because first of all, it got me through the interview. Secondly, I really used the stuff that you taught me all the time in my job. And I don't remember what the last thing was. But anyway, those two things are enough. This is like interview. The stuff that we cover in this class is like interview questions. You know, they're not going to ask you to write code. Well, they will ask you to write code, but they aren't going to ask you to write code that's compiling on a machine. They'll ask you to think about abstractly about a problem and give them a solution. That's what this course is about. Finally, you become modestly skilled at C++ and Unix, but that's, again, like I said, largely on your own, and that's a good thing. It's not a bad thing. I know you think I'm topping out. Well, I know you won't. But we have enough stuff to cover without doing that. Oh, I have to tell you, though. If you're worried about C++, there's C++ review sessions that are happening really soon. Like this weekend, starting on Sunday. Sunday, Monday, Tuesday nights. Go to Piazza, sign in, and there'll be a schedule. Cinda is going to go and give a lecture on C++ boot camp or something like that. That was a very quick introduction to C++ over these 3 evenings. And you can go to all of them, you can go to one or the other. There's going to be new material in each one, but you know, you'll see how much benefit you get from them. I can't believe I forgot that. Anyway. And you are thinking to yourself, why in the world don't they just record that and put that up on the web? And that's a great idea. Yeah, except for one small problem, which is that every time we try to record it, the recording breaks down. So the first time, the first lecture, no sound. Second lecture, no picture. What are you going to do? So anyway, this time we're going to try to record it again, and hopefully it all works out. Okay, questions about the course? I know I'm forgetting to tell you something, but I don't remember what it is. Yeah.
Do we have any homework that this week next?
Do this week? No. Next week? Yes. Friday. And end of Friday. Friday midnight. Any other questions? Yeah.
So what time and where are the sequences?
What time and where is completely unknown to me because I know, for example, the room has not been set yet. We're waiting to find it. Hopefully it's in the swing space.
So it just be posted on Piazza?
It'll be on Piazza. Yeah. Yep.
Are the homeworks on edX or like campus or like other systems?
Okay, I'll tell you. Because you're going to eventually have to know. The homeworks are on Overleaf. Oh, I hate Overleaf. It's terrible. Okay. Plus, you have to learn a programming language to do your homework. It's written in LaTeX. Oh, that's going to be terrible. It's not. It's going to be great. Because, first of all, there's nothing better than LaTeX for typesetting mathematical equations. And let me just tell you on your first homework, there are lots of mathematical equations. And it's easy to do in LaTeX. Plus, we'll give you the entire document, which is your homework, in LaTeX. And all you have to do is type in the answers. So it's great. And you're learning LaTeX, which is great. And there's got to be another positive that I haven't thought of yet. But it's an incredibly great collaborative environment for doing homeworks. For us, for this particular course. Because otherwise, we get... Anyway, you don't want to know. years have passed, there have been problems with understanding what people meant. Yes?
When do you offer those stuff?
When do my office hours start? Do I have office hours today? Not today. So whenever it is, like tomorrow morning. Today I have a TA meeting right after, not this, but the next one. Okay, good. Great. Holy cow. Okay, we got to speed up. This has been fun, but let's go faster. We're going to analyze algorithms. We're going to analyze them for correctness. We're going to analyze them for understanding whether or not the algorithm can be improved. We're going to analyze them so that we can get an idea of how much time they take. That's the running time of the algorithm. The number of steps that it takes as a function of some parameter n, which measures the input size. Like in Rogers Arena, it might be the number of people in Rogers Arena. And we want to understand how our algorithm runs, how much time it takes as a function of that parameter n, for example. That's what we're up to. And so you might ask, does it really matter? So I've listed some running times down on the left-hand side here. There's a running time as a function of n, the input size, that's log n. N is another running time. N, for example, is a running time of your sequential search in Rogers Arena, which has to go to every single person in the entire arena. That takes time n. There's n times log n. That's if you wanted to sort all the people in Rogers Arena. That's how much time it would take, would be n log n. There's n squared. N squared is if you wanted to compare every two people in Rogers Arena together and say, everybody pair up and ask each other if they're Roger. That's a crazy algorithm, but it takes time n squared. And then there's something which is 2 to the n, which is like, let's try all orderings of people in Rogers Arena. All possible different order, well, let's just take all subsets of people in Rogers Arena, not all possible orderings, but all subsets. And we'll look at those subsets and we'll see where Roger is. Maybe he's the only one in the subset. So that would be 2 to the n. And if you look at the running times on a computer that executes one operation per picosecond, by the way, that's pretty much the computers that are around today. Do you know how far light travels? How much time does it take for light to travel 1 millimeter? 3.3 picoseconds. That's how fast your computers work. It's working pretty good. Okay, so you got your picosecond, trillionth of a second. That's 10 to the minus 12th. Okay, and look, everything's done before 1 nanosecond, which is 10 to the minus 9th nanosecond. I'm doing this because I don't know if you guys know the names like nanosecond, picosecond, millisecond, microsecond. You guys know all that already? I never learned this, really. So that's why I feel obliged to teach you. Nanosecond, like see, I think it's 10 to the minus 9th, but you can correct me if I'm wrong. Okay, that's if n, the size is 10. That's how fast these programs are. They're blazingly fast. So if, on the other hand, you went to 100, then now everything increases. As you can see, the log n goes up by 1, the n goes up by to 100 picoseconds. N log n is about 2 times 100. Is the first two rows multiplied together. N squared is now 10 nanoseconds. And down here at 2 to the n is 1 exasecond. An exasecond is 32 billion years. Wow. Don't use that algorithm. Okay. That's a long time. If you increase to 1,000, it gets slower. There's microseconds now. If you increase to 10,000, things get slower. But still, look at this. 100 microseconds, I blink, it takes me 300 milliseconds. I blink really slowly, it takes me about a second. I'm not going to worry about this. So why should you worry about running time? Look, computers, that's about as fast as they're going to be, really, unless you go to parallel computers. But look, 10 milliseconds, nothing. What are we worried about here? Why do we have this class about efficiency? Ooh, that's not good. If I get up to inputs of size 10 to the 9th, and I have an n-squared algorithm, it takes a week to solve it. Can you think of anything that's 10 to the 9th? It's inside of you.
Number of cells in a human body.
Possibly. I was thinking of your DNA. Your genome is about 10 to the 9th. If they want to find something in you, if they want to compare you against the healthy sequence, they have to do that comparison. If it takes n-squared time, you're waiting a week. So one of the reasons why they were able to sequence the human genome is because the algorithms they were using were not n-squared algorithms. They could do things faster than that. And so for that size problem, what else do you know that's 10 to the 9th? Anything, any data in this world is growing to be that big, except for number of people, and we're getting there. We're in the billions. But large, when it gets big, running times matter. So we're going to be interested in running times in this course as well. Okay, we're done. I will see you on Friday.